Okay, second video. So we've got our stored energy based on position. Now, when it comes to putting this all together, we can talk about potential energy and kinetic energy as mechanical energy. And that's what we're going to be talking a lot of. In general, we can say that there's this law of conservation of energy, and that being energy cannot be created nor destroyed. It can change forms. Now, what do we mean by that? Literally, it can move between motion energy and stored energy. However, we learned in thermodynamics last year that whenever energy changes forms, that some energy is lost to an undesired product, usually in the form of heat, that we can't kind of get back and use in a mechanical sense again. Now, in 1905, Einstein releases his most famous equation in his topic of special relativity, and he has discovered that the relationship that energy is really a form of mass, and mass is really a form of energy, that equation being E equals mc squared. So E is energy, m is mass, c is the speed of light, which is 3.00 times 10 to the 8th, which is the fastest anything in the universe can go. And therefore, energy and mass are really the same thing. They're two sides of the same coin. So, I said we were coming back to work, okay? And this is definitely an important idea to get at so that we can keep this in mind. Work, okay, is energy transfer. It literally is the way we move energy between forms, but done a specific way, and that would be by applying a force as the object is displaced. Okay, that's our definition. All energy, so work included, is a scalar quantity. This basically means that if you have positive energy, if you have positive work, you have gained energy. If you have negative work, it means you have lost energy from the system. Its units, like all units of energy, are joules. Now, we're going to do a little bit about talking about this idea of how you multiply vectors together, because we talked about the idea that what we have is that work multiplies a force vector and a displacement vector, okay? And so meaning we have direction times direction. Not getting into the whole math of it all, but suffice it to say that when we're looking at these, you can't really multiply left times right, or like north times north. Like, what the heck kind of direction is that? Like, north squared? Like, not a thing. Okay. This is a way, okay, the dot product is a way to take only the parallel components and you get a scalar product, meaning you get a product or a multiplication whose answer is directionless. Okay. So simplifying it out in doing all of the math would simplify to our work is FD cosine theta, where work is, W is work, F is the magnitude of the force in newtons, D is the magnitude of the displacement vector, and theta is the angle between them. It's going to make a whole lot more sense once we actually start looking at this in terms, sorry about that, wrong way, in terms of doing the example problem, which we're going to do now. Okay, so in this example, we have a 15 kilogram box sliding across a rough floor that is horizontal and is being pushed by a force of 29.4 newtons for 3.00 meters. Now, so when we ask what is the work done by the 29.4 Newton force, I am going to kind of start, or one way we can get started on this is looking at all of the forces acting on the box. So I've got, and I'm not going to make the time to actually like make the full free body diagram and everything, because what we see over here, that axis, is not for a free body diagram. It's rather for a vector diagram. And so this is going to be the force of friction over here. So we've got a normal force, gravitational force, a pulling force, and a frictional force trying to slow it down. So if you notice when we have the what is the work done by the 29.4 Newton force, you have this step-by-step. Start by drawing the force vector and the displacement vector, each starting at the origin. Okay, I'm going to put my 29.4 Newton force of the push, okay, and in my displacement vector is also to the right, okay, so that's that 3 meters, okay. Now, super important question for you, right? What's the angle in between right and right? 0 degrees, I agree wholeheartedly. So we need to write the generic equation that work done by the push would be the force of the push times d times the cosine of the angle in between them. So, and then we need to plug and chug. So we've got 29.4 times 3 times the cosine of 0. Well, like cosine of 0 is just 1. 29.4 times 3 is 88.2, and that means the work of the push is a positive 88.2 joules, meaning the push adds energy to the box. Next up, next question is, what's the work done by the frictional force? Well, we still have that, our frictional force is in the opposite direction of the motion of the object, and our displacement vector is still to the right. You are going to notice that I intentionally put my force vectors and displacement vectors as different colors. Why? So that I can tell them apart. And the angle in between left and right, I agree, it's 180 degrees. So what's the work done by the frictional force? The work done by the frictional force would be the force of friction times d times the cosine of the angle in between them. Well, wait a minute, we weren't given the force of friction. So I'm going to need to use my remembering skills and say force of friction, there was an equation on the equation sheet, and we said that that was just the mu times the normal force. Now, and we're like, crudsickles, we got to go back and do our normal force. So we've got our force of friction here, we've got our force of our pull, the normal force was going up, and mg is going down. Well, if we're looking at just the normal force, that means we're looking at something vertically, and we can say A in the vertical direction is 0. There's no acceleration, there's no motion, which means forces up have to equal forces down. So the force normal is just mg. Well, that's cool. So I can come back here and kind of quickly say that, oops, sorry, that should be the normal force. So that would just be mu times mg. Plug that sucker in. Work of friction is mu 0.2 times the normal force, which is m of 15 times g, 9.8, times the cosine of 180. All right, well, cosine of 180 is -1, so we just get a negative, punchy in our calculators, and we get negative 88.2 joules, which means friction removes energy. Huh. This seems like something we kind of maybe talked about early, like, I don't know, just friction removing or slowing. This just seems kind of familiar. All right, enough of that. Work done by the normal force. Okay, all right, moving on. Normal force, straight up. Our displacement to the right. And again, what's our angle between right and up? That bad boy is a 90-degree angle. So the work done by the normal force would be the force normal times d times the cosine of the angle in between them. And hey, we just figured out that the normal force in the last slide we figured out was mg, so we've got mg times d times the cosine of 9g, cosine 90. Isn't that just 0? So mg times d times 0 means the normal force does 0 work. So the normal force does not either add or remove energy to the box. All right, and finally, what's the work done by the gravitational force? The last of the forces we identified when we were talking about all the forces acting on the box. So we've got the force of gravity, we've got D. Hey, isn't this angle also 90? So the work done by gravity would be the force of gravity times D times the cosine of 90, which we know is just 0. Again, gravity does not add or remove. Energy from the box. Okay, so last question. Okay, what's the total or net work done to the box? Okay, I want to take you through the easy way to do this, and then we can talk about the hard way. All right, when you're talking about the total or net, it just means the sum of the works. Now, because this is a scalar, we don't have to worry about left and right and all of that. So it's literally just work 1 plus work 2 plus work 3 or whatever. So here we can say it's the work done by the push plus the work done by friction plus the work done by gravity plus the work done by the normal force. Now, we already figured out that those guys, that the gravity and the normal force were 0 because they're at an angle of 90. And the work done by the push is positive 88.2, and the work done by friction was negative 88.2, leaving us with a net work of 0 joules. Okay? So I'm in this situation, especially when it's in that the 0 and O can look very similar. So I have a strong tendency to write it as 0.0 so that it doesn't look like OJ in my notes. Now, we could go through the whole process of figuring out what the net force is and marking the net force and marking the displacement and saying that work net is F net times D times the cosine of the angle in between them, but I'm going to be honest, I don't want to bother with that, okay? Adding up the works I already found, definitely the way to go. Okay, if there is still time in class, please take a look at numbers 1, 2, and 5, but you don't need to finish them for homework, only work on them in class. Thanks.